at the cathode. Here you have OH minus. It must be noted that for every OH minus, to get the equivalent oxygen, it has to be 4 moles of hydroxyl ion. So you have 4 moles of hydroxyl ion giving rise to 2 waters plus 2 oxygen. So this is a balance for this. For every 1 mole of hydroxyl ion, it has to be 4 mole that will give you the respective oxygen gas. So in that situation, oxygen is liberated. So in the electrolysis of acidified water, hydrogen gas is discharged, is liberated at the cathode, while oxygen gas is liberated at the anode. Faraday's laws of electrolysis. We have the first law of Faraday and the second law of Faraday. The first law of Faraday states that the mass of an element liberated or discharged during an electrolysis is directly proportional to the quantity of electricity passed into the electrolyte. What are we saying? What we are saying is that the mass is directly proportional to the quantity of electricity passed. So if this proportionality constant is changed to equal sign, it goes along with a constant Q, where M equals to the mass of the element, while Z is the electrochemical equivalent, is a constant, while Q is the quantity of electricity. So mathematically, Faraday, by first law of Faraday, it is denoted that your mass is highly proportional to the quantity, which that same mass is equal to ZQ. So that is the first law of Faraday. Second law of Faraday. Faraday's second law states that when the same quantity of electricity is passed into different electrolytes, the relative number of moles of the elements discharged or liberated are inversely proportional to the charges on the ion of the elements. What are we saying by that? A case whereby you have your sodium, which is a metal. Here, when it ionizes to give you this, here it is 1 atom of sodium and the charge on it is 1, meaning that 1 electron on it is equivalent to 1 mole on it, and 1 mole is equivalent to 1 Faraday. That means for each electron that is discharged or lost is equivalent to 1 mole and is equivalent to 1 Faraday. And 1 Faraday is 96500 coulombs. That is the unit of electricity. So that means for sodium that is donating 1 electron, it's equivalent to 1 mole and it's equivalent to 1 Faraday. For calcium that is losing 2 electrons, it will be 2 electrons, which is equivalent to 2 moles, which is equivalent to 2 Faraday, which is equal to 2 times 96500 coulombs. So this is all about the second law of Faraday. Calculations under the first law and the second law of Faraday. Number 1, calculate the mass of silver deposited when a current of 2.6 amperes is passed through a solution of silver salt for 70 minutes. Given that the relative atomic mass of silver is 108 and at 1 Faraday. Here, if we want to solve this calculation, the first thing we have to do is to write down all the known parameters. So from the question, it can be interpreted as I, which is the current, is given as 2.6 amperes. Also, the time is given in 70 minutes. And mind you, working under the first and second law of Faraday, the basic or the standard unit of time is in seconds. So that means that this 70 minutes has to be converted to seconds. And if it is converted to seconds, it will be 70 times 60. Everything will be in seconds. And when that is done, it will be 0, 0, 4, 2. So you have 4,200 seconds. 4,200 seconds. And going by the second law of Faraday, it is noted that silver ion with one electron is equivalent to silver metal. Here, since silver has lost one electron, for every one electron lost, you have 1 mole of that silver, then you have 1 Faraday. And since the question asks us to calculate the mass of silver deposited, and the relative atomic mass of silver has been given in the question to be 108 gram. In this situation, we know that the quantity of electricity is equal to IT, which is also equal to, what is I from the question? 2.6 times, what is T? T is 4,200 seconds. That is the quantity, everything in coulombs, the unit of electricity. And since our interest is to look for the mass of the elements, that is the silver deposited, it can be deduced that 1 Faraday of silver, which is equivalent to 96500 coulombs of silver, gives 108 gram of silver. Then the quantity that is used in the process is 2.6 times 4,200 coulombs of silver. Then the mass is unknown, let's say X gram. So mathematically, you have 96500 coulombs of silver, which is equivalent to 108. Then 2.6 times 4,200 coulombs of silver is now equivalent to X. Our interest is to calculate the mass of this silver that is deposited by this quantity of electricity. So in that situation, what we have to do is to cross multiply. We cross multiply. So when we cross multiply, we have 96500 times x is equal to 108 times 2.6 times 4,200. So in that situation, since our interest is to look for the value of x, we divide both sides by 96500 coulombs. And once we divide that, we will have our x to be equals to 108 times 2.6 times 4,200 all over 96500, and at the end we're going to have 12.22 gram. What am I saying? So it will require the mass 12.22 gram to deposit this quantity of electricity. So that is the answer to question 1. Question number 2. Calculate the quantity of electricity that will be required to liberate 4 grams of oxygen gas during the electrolysis of acidulated water. We have established this when we were doing the analysis of acidulated water. There, it was obvious that the cathode hydrogen gas was discharged, hydrogen ion was